Electric cars like the Ford Mustang Mach-E have become more and more popular for their lower CO2 emissions. However, cooling such cars poses an interesting technological problem. In fact, both the cabin and the car battery must be kept cool. Our goal is to create a fully functional cooling system for an electric car to be used in Saudi Arabia, a particularly harsh environment. Our goal is to keep the cabin temperature at 25 degrees and the battery temperature at 10 degrees. Heat loads are mainly invaried. In fact, heat may creep in through conduction or even convection. Heat may be generated by the passengers inside the car or even the batteries themselves. But our calculations showed that most of the heat comes in through radiation, through the windows. We studied many different refrigerants. In fact, R134A is the reference in the car AC industry. However, it is being progressively ruled out as it is quite unenvironmentally friendly. That's why we took a look into R1234YF, which, even if it's more flammable and costly and harder to work with, is more environmentally friendly. We took a look into natural options like CO2, ammonia, or water. Once implemented into our system, they showed low performances. In the end, a single-stage cycle was chosen. It was comprised of a compressor, a heat exchanger, a condenser set at 64 degrees, and two evaporators, both set at 10 degrees, one for the battery chiller and one for the cabin, so as to better suit the needs of each of them. Double-stage systems were investigated, but the improvements they offered were simply too minor in regards to the cost they would occur. Sizing the compressors proved difficult. In total, 11 compressors were compared. The required revolution speed needed to meet our system's mass flow requirement was calculated, and it was noticed that scroll compressors displayed high efficiency. In fact, electric scroll compressors proved really interesting as they can easily be implemented into an electric car. Finding the right heat exchangers to be used into our car was also complicated. It was both hard to find accurate models for them given our quite unique problem, and also find heat exchangers that could actually fit into our car. In the end, our results made us settle for heat exchangers with microfins for both the cabin evaporator and the condenser, whereas a plate cooler was chosen for the car battery chiller. In the end, our real cycle, with all the different components taken from the different manufacturers, proved to be slightly less efficient than the one we had theorized. In fact, we had critically underestimated the heat losses and efficiencies involved in our cycles. However, we still needed to control our own system so as to be able to meet the cooling demand at a given moment. We knew the cooling was determined by the refrigerant mass flow in the system, which in turn could be controlled by the compressors. We designed the speed control of the electric compressor so as to be able to quickly meet the required cabin temperature. When the AC isn't needed and only the batteries need cooling, a simple on-off system control of the compressor is used, since the compressor is inefficient at very low speeds. Hence, the COP of the system may fluctuate with the moment, the needs, and the seasons. This project proved very challenging, but it taught us many things in both heat transfers, modeling, thermodynamics, control, compromise, and optimization.